Okay, so this week we are going to wrap up Module 4, and you'll have your Exam 4 on Wednesday. And so that's going to cover substitution, which is radical CH to C halogen substitution, SN2 and SN1. So we'll wrap up the SN2 stuff today with stereochemistry, and then kind of talk about the general features of SN2, and then move into SN1, and that deals with the substrates that have tertiary halogens. So there's going to be some, I guess, orthogonality to SN2 versus SN1 in terms of how the things are classified and what solvents you use, and the mechanism is a little bit more involved, but it's still a substitution. So we wrapped up last week with looking at installing the different elements, carbon, nitrogen, oxygen, as nucleophiles, which relates to the functional groups, and then you need to review the unique spectroscopic signatures of those functional groups. The substrates that we used, or the electrophiles, were all methyl derivatives. So we were using bromomethane. If you use a primary halogen, you don't have to worry about this next issue, which is stereochemistry. So this only arises when the electrophile has a secondary leaving group. For SN2, we're not concerned about tertiary carbons, so really we're just narrowed down to secondary for this part. And the substrate that we're going to look at to demonstrate this is now this 2-bromobutane derivative. And so you'll notice that the bromine is shown with this wedge, so that means it's coming out towards you. And then there's a hydrogen going back. So this is a stereocenter. And due to the mechanism of the SN2 reaction, where the nucleophile attacks the carbon bearing the leaving group at a 180-degree angle, there's inversion of the stereocenter. As we go through this and you do problems, we'll talk about the CIP designation of R and S. For the most part, when you make an assignment of R versus S, then you do an inversion. It will flip one way to the other. But you do have to be careful with just assuming that, because the nature of that nucleophile will matter, like what element is bonding to the carbon. So we'll run through the algorithm for determining that, but just to show some arrows here. So our nucleophile is of that form. We have a cation and an anion, so it's a strong nucleophile. We're using a polar aprotic solvent, acetone, which is a ketone, and then 60 degrees. So our secondary bromide will be attacked at that carbon. The bromine's the leaving group. Sodium bromide is the inorganic byproduct. And then we've done this substitution of bromine for azide. So what you'll notice is that of that stereocenter, now the azide is attached with this dashed bond. So bromine was out towards you, and now azide is away from you. With the drawing nomenclature, that means that the center has inverted. So when you look at these things, it's not necessarily always going to be that straightforward to determine that it has inverted. So let me just highlight some things here. So there's the wedge, and here is the dash. So wedge is always out towards you, dash is away from you. So with just the bond drawings, you can see that it's been inverted. Now, we still have to validate that using the nomenclature. That's the R and the S that we assign to the carbon that's bearing the 4 different substituents, and then we use the atomic numbers from the periodic table to assign priority. On the next slide, we'll actually do the assignments to each of these, but again, don't assume that if you start with R, it's going to go to S, or if you start with S, it's going to go to R. And the reason you can't make that assumption is because the atomic numbers of the leaving group, so in this case bromine versus nitrogen, you still have to look at those and do the priority rules. So let's just make the assignments now. So what is the CYP designation for the 2-bromo and the CYP designation for the 2-azide? So here's our stereo center. We have a carbon with 4 different things: a bromine, an ethyl group, a methyl group, and a hydrogen. So when we assign priorities, we look at, again, remember the directly attached atoms. So bromine will be priority 1, hydrogen priority 4. The remaining carbon and carbon, since they're equal, we have to consider all 3 things bonded to it. So this carbon will win because it has another carbon. So that's going to be 2. That'll be 3. The lowest priority group is pointed away from us as the dash. So we go 1, 2, 3. That's clockwise, so this should be R. That center will be R. For the product, we end up with the sort of same rotation in a sense. Hydrogen's 4. In terms of atomic number, nitrogen is greater than carbon, so that's 1. And those other 2 carbons stay the same. So it's still going clockwise, but now the lower priority group is out towards you. So we flip the R to S. And then we would end up with D is the correct answer. So you see the inversion again with how the bonds are drawn, and that inversion is also witnessed here with the CYP nomenclature R to S. What I said, though, is based on the nature of your leaving group and nucleophile, sometimes those priorities don't always invert. So if you start with R, you can still end up with an R. And that's the nature of what those elements are and how you do figure out the SIP designation. So my point of all that is still go back through no matter what the product is and assign priorities. So let's look at this in another example where the leaving group is drawn slightly different now. So the leaving group is in the plane, and all the other substituents are presented different. So we have a secondary bromide. That carbon is a stereocenter. We're going to use sodium hydroxide as the nucleophile, and we want to figure out what is the name of the product. So one way to think about this, since it's SN2, the nucleophile has to attack opposite to the carbon-bromine bond. And then when we draw the product, we're going to keep that in the plane because the CBr bond is in the plane. Then these other three substituents, hydrogen, methyl, and then this carbon chain, we're just going to invert and draw them all over to the right side. So since the H was in the plane, we're going to leave it in the plane. The methyl was coming out towards us, and then the rest of the chain was going back. So that would be one way of showing the product with the inverted stereocenter. So now what we have to do is figure out what the correct designation is. So the numbering in blue is the carbon chain numbering. Since it is a substitution, we can't have bromine in it anymore, so we can eliminate that one. Once we've numbered the chain, we can see where the alcohol is, so we can eliminate D. And then we're left with the 2-octanol, where we have to figure out if it's R or S. So what do you think it is? What? So the right answer is S. So the way that I do this, I've taught this slide for a solid 6 years now, so it's kind of memorized, but that's the lowest priority group, that CH. If you put your eyeball like down here, because then the lowest priority group is pointing away. The oxygen's 1, this carbon is 2, and that carbon is 3, and you'll go counterclockwise, so that'll give you S. So again, the challenge with the way that this one's drawn is the lowest priority group is in the plane. You need it pointing away from you. So the easiest thing would be to just make a model and then kind of rotate the model. But if you can imagine putting your eye here, then it's directly opposite that lowest priority. So when you do that, the oxygen becomes priority 1. This carbon is 2, and then that carbon is 3. So when you connect those, they'll go counterclockwise.
Would you not look at 2 as like the whole chain? So
In a sense, yeah, when you look at carbon versus carbon, to assign priority, you then go out. So that carbon has 3 hydrogens. This one has 2 and then another carbon, so that's why it gets priority 2. The challenge really is, if you don't have the model kit, being able to visualize how that rotation is happening. Any questions? So true or false, the measured specific rotation, either plus or minus, is dependent upon the R or S designation. So that one is false. And really, it comes down to it's measured. So it is what it is by how it rotates the plane polarized light. The RRS is just a tool that we use to name these things. You don't need an instrument to do that. You can just look at the structure, follow the rules. You can assign R and S. The sign, you're either measuring using a polarimeter or that data will be given to you. So based on what we've learned regarding the kinetics, the solvent, and nucleophile strength, what are the best properties to make one of those reactions successful? So we can eliminate B because the 2 stands for bimolecular. And then the solvent needs to be polar and aprotic. So that'll eliminate A. And looks like it eliminates D as well. And then the nucleophile strength has to be strong. So that's, again, of the form this cation anion ionic bond. So the lone pair can be exposed. So if you think of this as a conjugate base, its acid form will always be a weaker nucleophile because the lone pair is tied up in a covalent bond. If the free energy of activation of an SN2 is positive, so from your starting material energy well, you're typically always going up and over the energy of activation, but the overall free energy is negative. What term describes the thermodynamics of the process? So this one is B, And again, the reason it's not called exothermic is because we're using this Gibbs free energy that includes the temperature and entropy components of the measurement. Any astronomers in the crowd? I want to explain what bathochromic means. So here's the table to wrap up the SN2 discussion here. So we have promoting factor. Here's our SN2 column, and then we're going to transition into SN1 and then fill that column out. And so what you'll see in terms of these trends, some things are similar, but most of them are kind of orthogonal in the sense of the trend flips. So our electrophiles, methyl is greater than primary, is greater than secondary, and tertiaries do not react. These special cases will enhance the rate. So if you have allylic or benzylic secondary, that will probably react faster than if it's just a methyl or primary. Leaving group abilities in terms of the halogens, iodine is greater than bromine, is greater than chlorine. And then of those sulfonate esters, where an alcohol has been activated, the trifluoromethyl is greater than the methyl, is greater than the para-toluene sulfonyl. So these were made from alcohols because OH minus is a bad leaving group. You activate it, now it's a good leaving group. Nucleophile strength. So strong nucleophile, and of that, the anionic form is greater than the neutral form. And if you think of that as sort of like an acid or conjugate base pair, then that should make a little bit more sense. Solvent type, we want polar aprotic. The polar part supports the charge development in the transition state because we're going through this wacky looking 5-coordinate carbon atom where we have these delta minus charges. The aprotic part helps sequester the cation. So the M plus of the nucleophile. So the polar aprotic part surrounds that cation. The nucleophile has the lone pair, which is more exposed for bond formation. The kinetics, that's the 2 of the SN2. So it's bimolecular, it's second order, meaning that the overall rate depends on the molar concentrations of both the nucleophile and the electrophile. For secondary substrates that have a stereogenic center, there will be complete inversion. But remember, I'm still harping on you have to use the SIP rules to determine R and S. The bond wedge dash, that's sort of straightforward in a sense. But based on what your nucleophile is relative to the priority of the electrophile, you still have to apply the SIP rules. This new thing, rearrangements, is really what we're going to talk about in SN1. So there's a fresh layer of hell in the learning here. Mechanistically, SN1 is more complicated because along the reaction coordinate, we have to ask some more questions to see if a rearrangement can occur. due to the bimolecular rate nature of SN2, where the nucleophile has to attack the electrophile for the mechanism to occur, that leads to the inversion. The SN1 mechanism is a little different. So it just doesn't kind of go through one transition state, but many transition states. And from that, you can have these rearrangements occur. So the way we classify things and how we look at the conditions, the solvent, the nature of the electrophile is important, because ultimately it helps you decide which mechanism is operating, and then what of these factors you need to consider. So we're going to move along with the rest of today and on Wednesday to fill out this table looking at all these factors. The key word, I think, really that you don't want to lose track of is substitution. You have some group and it's just being substituted for another functional group. And practically speaking, you again want to always refresh your memory on the IR, mass spec, and NMR of these functional groups. So for SN2, when we're classifying the leaving group in the electrophile, the rate occurs such that methyl was greater than primary, was greater than secondary, and tertiaries did not react. So those were two hindered. But that does not mean tertiary substrates never undergo substitution. So they do, they just use this different mechanism. So the key difference here is the reaction now is SN1. So that still stands for nucleophilic substitution. The rate now is unimolecular, and that's totally dependent upon the electrophile, so the thing bearing the leaving group. So how do we get these tertiary ones to react? We change the solvent and the nature of the nucleophile. But whatever that leaving group is, it's going to get substituted. So perhaps something that may make it a smidge less complicated. The solvent for these is typically the nucleophile. So when you're looking at how do I know which one is occurring, SN2 or SN1, you'll get a sort of intuition developed when you look at these. You will not see a strong nucleophile present. So based on what these solvents are, another term for the mechanism is solvolysis. So we know what hydrolysis is, that's cleavage by water. Solvolysis is cleavage by solvent. So our SN1 rate now is flipped. So tertiaries react faster than secondaries, and essentially primaries, unless they're allylic and benzylic, do not undergo this mechanism. So that one right there is the one that overlaps and where you really have to sort of read into the conditions that are present. in terms of how you're deciding how the mechanism proceeds. And that then gets to, is there this inversion of stereochemistry that's happening, or this other new thing, rearrangements, and how does that affect stereochemistry? So the model reaction that we're going to look at is shown, and you may have already done this in lab a month ago. I do not know. You're probably wondering then, what is this useful for? So we're going to take tert-butyl bromide. So that's this thing right here. That's a tertiary bromide. And we're going to react it with ethanol. So ethanol is both the solvent and the nucleophile. So the bromine's the leaving group. It's going to leave, and it's then substituted for this O-ethyl. So here's the leaving group, and it's undergone a substitution. So the new functional group that we've formed is an ether. So the SN1 reaction, unlike SN2, really can only, practically speaking, generate 3 types of functional groups: ethers, esters, or halides. So you can't use any willy-nilly nucleophile you want, because the way the reaction proceeds, where the solvent is the nucleophile, that restricts the functional groups we can access in the product. So that's the overall transformation. And what we'll see on the next couple slides is that the reaction coordinate is a little bit more complicated due to how the leaving group leaves. To give you a preview of that, of our tertiary substrate, we know that the difference between carbon and bromine, based on electronegativity, we can assign bromine as delta minus, and then carbon's delta plus. Under the SN1 conditions, that carbon halogen bond will ionize. And so that means it's going to form 2 ions, because bromine is already hoarding some of that single bond electron density. We can just cleave that bond. So this is a homolytic bond cleavage. Those 2 electrons go to bromine. So we formed 2 ions, a carbon cation, that's called a carbocation, and then a bromide anion. Notice that the charge overall is balanced, plus and minus. So we start with neutral. The charges over here are balanced, so overall they're 0. the universe itself will not allow you to form an excess of any one charge. So when you're doing that, you got to make sure that everything still balances out. That process is the rate limiting step, how that carbon leaving group sigma bond ionizes. So rate limiting means that is the highest hill in the energy coordinate. You have to put a lot of energy to get over that hill. Because of that, it's the slowest step. And what you'll notice is we did not invoke the presence of the solvent in terms of a collision yet. So that's why it's the 1. So 1 means unimolecular. So really the rate only depends on the concentration of the electrophile.
Depends on the concentration of the electrophile, you said?
So here's the ionization. So that's the slow step. We start with a tertiary substrate. The carbon is sp3 hybridized. When bromine departs with those 2 electrons, the carbon hybridization changes. It goes from sp3 now to sp2. The plus charge resides in the empty p orbital. And so I'm using this word intermediate because along the transition or along the reaction coordinate, an intermediate will live a little bit longer than a transition state. So when I think of transition states, I always think of the word partial. You have partial bond breaking, partial bond forming. An intermediate, it's reactive, but there's not partial things about it. It can live a little bit longer, and because it lives longer, that allows it to do other things that are not possible in the SN2 reaction. So the carbocation here, we have this p orbital, which is dumbbell shaped. So that positive charge is dispersed equally amongst those lobes. The solvent, which is the nucleophile supplying the electrons, will attack one of those lobes. That means the carbon, now that it has 4 bonds, goes back to sp3. And what this does is generate another intermediate because the plus charge is now on oxygen. So that's called a oxonium, which shouldn't be terribly unfamiliar to you because we've talked about hydronium. So the difference here really is of hydronium, we've replaced an H now with some carbon groups. So the oxonium ion, that has a certain pKa value. It undergoes an acid-base reaction, and ultimately we do the substitution. The take-home message is whatever your solvent is, whether it's an alcohol or a carboxylic acid, that part of it is what is ending up in the product. The solvent slash nucleophile, you'll notice, see how it's of this neutral form? There's no negative charge on it. So the lone pair is coming from sort of the neutral oxygen. The result of that, when you form this intermediate, it still has to undergo one more step to become overall the neutral product. Any questions?
Yes. If give me a second.
So the oxonium ion is also an intermediate.
Yes.
Okay, if the nucleophile is attacking this compound without the leaving group, does that mean isomers are going to be created since it can attack it at different angles?
Yeah, so basically this relates to the question of the stereochemistry. With the SN2 reaction, only secondary substrates that had an existing stereo center would undergo inversion. If you have a tertiary substrate and all of these things are different, so it does have a stereo center, when the hybridization changes, these three groups here, so that 1, 2, 3, they all lie in a plane. And the p orbital is sort of sticking out from that plane. So the nucleophile can attack either side. So ultimately, if you started with, say, a single R or S stereogenic center, that stereochemistry will racemize. So you get a 1-to-1 mixture of R and S as your substitution products. So this, to the best of my drawing ability, is what a reaction coordinate looks like for an SN1 reaction. So notice it's got a lot more peaks and valleys than the SN2. And so the question is asking you, how many transition states are there? How many intermediates? And then what is the overall delta G value? So how many transition states are there? So there's 3. So we can eliminate A and D. And then how many intermediates are there? So there's got to be 2. And so from where we started using this dotted line to where we end up, is that exergonic or endergonic? So that's exergonic. So we're starting at some energy, we're going lower, so that means heat is released. So we would end up with B is the correct answer. So just to review these real quick, we're starting at some energy as a well or a trough, however you want to think about that. We end up somewhere, some other energy level for the products. And then along the way, the highest point on the path, those are always transition states. When you get into a well, those are called intermediates. And again, this isn't the best representation, but when the ball goes up the hill, even though I'm showing that as kind of a nice sort of slope you can stand on, the time that chemical species, the transition state, can exist is very small. So it either wants to roll back down this way or this way. So the time element here is sort of like the derivative in calculus. It like flips immediately. When the ball is in the well, it can roll back and forth, meaning that its existence in time is a little bit longer. And that is what leads to one of the complicating factors of the SN1, the fact that it can exist longer. But from there, it can move forward through another transition state, another intermediate, another transition state, and then finally to the product. So if we have all these transition states, how do we know which one is the rate limiting one? Really visually, when you're looking, it's whatever one is the highest from where you started. It does not necessarily have to be the first one that's shown. Like you could have a higher transition state later on. So anytime there's this electrostatic attraction between, like a lone pair and something delta positive, when things are coming together or there's these ionization events, if you're drawing arrows, you want to think about this as well, because every arrow you draw is another sort of peak or valley you can put in the coordinate. So here's the reaction of that coordinate with some structures laid over it. So when the reaction starts, this bond starts to ionize. And so that's represented by now, instead of a solid line, a dashed line, which means that the bromine is pulling away, that bond is getting longer. So it's going to get to the point, in that energy well, when we were talking about what a bond is. If they're really far apart, they don't know they exist, but when they get closer together, eventually there's that attraction, that's the bond that exists in this well. But as they move farther apart, in this case, they're two separate things now, a carbon with a plus charge and a bromine with a minus. So that's an intermediate. So notice reactive intermediates are almost always higher in energy than what you started from. In terms of the definitions, this is a Lewis acid. We have an empty p orbital that can accept electrons. The solvent is now going to come over and start partially forming an oxygen-carbon bond. So that transition state is the partial formation of that CO bond. Once they get close enough to form the actual sigma bond, that's another intermediate, because the oxygen is still protonated. The last transition state is a proton transfer from solvent, or from the intermediate to solvent. So you're you're breaking this existing bond, you're making a new one. And then once that happens, we end up with our product well here. So overall, from where we started to where we ended up, we went down, so that's the exergonic. I think one sort of learning injustice in general is, you know, when you look at this and you think in terms of space and time, you're like, well, you know, this should exist for however long. But again, it's really fast. You know, when I say reactive intermediate, it's not hanging around and going on holiday in Europe for 2 weeks. It's like sort of nanosecond time scale, if probably lower. Transition states are about femtosecond, you know, 10 to the negative 12, 10 to the negative 15 seconds in existence. Since these are a little bit longer, even though it's still a short amount of time, that little bit of time allows them to do other things. So in an SN1 reaction, the weak nucleophile attacks the p orbital. The p orbital is dumbbell shaped. So the reason talking about this is important is once you form that carbocation, those three substituents, whatever they are, bonded to that carbon, lie in a plane. Then you have that empty p orbital whose lobes are 90 degrees or above and below. So if you start with a stereocenter, that bond ionizes. The stereochemical information is lost. And the nucleophile can attack here or here. That will regenerate a chiral carbon in a 1-to-1 mixture of R and S. So in an SN1 reaction, the blank ionizes to a blankety blank with blank hybridization, resulting in complete blank of the stereogenic center. So the electrophile has to ionize to form a what? So that's a reactive intermediate that has to be a carbocation with sp2 hybridization that results in complete racemization. So the answer for this would be D. And so verbally, that's explaining the arrow pushing and then the outcome of the mechanism. So if we think back to that SN2 slide in terms of verbalizing the reactivity, the nucleophile attacks the electrophile at 180-degree trajectory to the leaving group. We have a single transition state, and then ultimately there's inversion of stereochemistry if there was a secondary substrate with a stereocenter. So now that we know a little bit about the mechanism, what are the solvents slash nucleophiles? And I kind of need to preface this based on the thoroughness of which these slides are ordered. So say we're starting with a substrate where the leaving group is a halogen. So some typical solvents slash nucleophiles we use are going to be carboxylic acids or alcohols. And these are arranged according to increasing dielectric constant. So acetic acid, ethanol, methanol, formic acid, and water. But really, any alcohol or carboxylic acid could be used for this. So if you use acetic acid as the solvent nucleophile, what you're going to end up with is an ester as the product. If you use an alcohol, you end up with an ether. So probably on Wednesday, what we'll get to, we'll look at where these X groups can be OH. So you can have tertiary alcohols that are good substrates for SN1. Again, the arrow pushing is a little bit different. In that case, the OH group can leave where, SN2 it can't, because the mechanism is different. So overall, these are polar, so that criteria is still there, but now these are protic. So protic really means OH. And so on the next couple of slides, we'll talk about what are the interactions with the leaving group in the electrophile with the polar protic solvent. Why do we need something that's protic now? So the rate limiting step is the ionization of the carbon leaving group bond. Generally speaking, they're polar covalent bonds to begin with, where we can assign this delta minus, delta plus, based on the difference in electronegativity. What the protic nature of the solvent does, so in general, we're just thinking about things with OH. There's an electrostatic attraction between that hydrogen, which is delta plus, and the leaving group, which is delta minus. So you can think of that as like a hydrogen bonding interaction. And again, the crappy thing about this drawing is I'm just showing one of these solvent molecules, but that bromine is sort of like a beach ball. It's surrounded by a lot of solvent. So you have a lot of these interactions tugging on that bromine. And since they're all tugging on it, you're further weakening that bond, which is helping to ionize it and overcome the energy needed for that rate limiting step. So as I said, that's your solvent, but it's also the nucleophile. So these are also called solvolysis, so cleavage by solvent. If we used the acetic acid, in this case, the product would be that substitution. So an ester is the main functional group. So I don't know how many labs you have left in this semester. Just one. Do you know what it is? What? It is this? Okay. So I know it's tough because you want to get in there and get out. If you have it at night especially, you want to go home and eat. But you know, when you're thinking about like the discussion in terms of yields and stuff like that, most students will say, you know, why is the yield low? Then you're like, oh, I knocked it over, I didn't weigh it out right. So those are kind of cheap excuses. But when you think about it mechanistically, you know, we'll call that our starting material. And so whatever weight it is, that's a molar amount. Typically with solvent, you always use an excess of solvent. So when you do your stoichiometry, figure out the moles of solvent that you're using, and you'll find out it's usually a huge excess. So the rate of this is really only defined by that electrophile because there's only so much of that. You know, even though you're incorporating some of the elements of that solvent into the product, your yield, theoretical yield, you're calculating from that. And since that's only present in a certain molar amount, overall the rate is going to be dependent upon how much of that you have in there. So, like stated another way, when you plug molarity concentrations into those rate equations, whether it's super concentrated or super dilute relative to the solvent is not going to affect the rate. So in terms of the trend, we had tertiary is greater than secondary, and primaries really don't go by this mechanism. So why is that? It's related to how stable the carbocation is. So a carbocation is a reactive intermediate. We need the leaving group to leave. And so a motivating factor for that is we're starting with something stable. We want this thing to leave. So how stable is the thing we're forming? If you think of that as going up these hills, the lower the hill you have to climb, ultimately the more stable that intermediate is. So tertiaries are greater than secondaries, and now primaries we don't worry about. But those two, allylic or benzylic, will enhance whatever class we're starting with. So we're forming, or we're going from sp3 to sp2 hybridization. So that positive charge lies in the p orbital. And the reason that tertiaries are the most stable, because you have stabilization of that empty p orbital by what's bonded to the sp2 hybridized carbon. Allylic and benzylic are special because once the leaving group leaves, that p orbital is next to an existing double bond. And that can be stabilized through resonance, as shown by this arrow. So drawn out more conventionally. That plus charge is distributed at the 1 and the 3 positions. If you have your average just Joe Schmo substrate, you're going to evaluate it according to just that trend, but you want to look out for these because of these resonance forms. So benzylic is now where there's the benzene ring. So that plus charge ends up in a p orbital next to the ring, which has those double bonds. And that just shows you that you can move that plus charge around a couple different places. So the more that it's kind of delocalized, the more stable it is. And so that is related to the rate because it's easier to form that. So those were the two special cases of allylic and benzylic. If we get back to the regular tertiary, secondary, primary methyl, how do we understand why tertiary is preferred? So these structures, that blue ball is meant, we're looking right down on the axis of the p orbital. So essentially what we're seeing is kind of like one lobe of that. So in this Newman projection, there's our p orbital, then we have this central carbon. It has 1, 2, 3 carbons to it. That's why it's tertiary. In this representation here, we're going to put our eyeball sort of looking at one of the carbons now. So we have a carbon in front. That carbon has 1, 2, 3 hydrogens. In the back is the p orbital and then the rest of the carbon substituent. So you see the p orbital lobes here. A carbon substituent, whatever is bonded to that, can align with the p orbital. So that CH bond, since it has electron density, is now aligned with something that's electron deficient. And so there's this kind of through space sharing of those electrons in a sense, or stabilization of the p orbital. And that can happen with all 3 of those carbons. So that leads to something that's stable. As you take away carbon atoms, so now CH3 to H, this H right here cannot overlap or align with the empty p orbital, so it's less stable. And then we just keep doing that to primary and then to methyl. So the rate decreases this way because you're losing stabilization. And there's a fancy word for this called hyperconjugation. It's kind of just like a through space effect. So methyl carbocations, for this class, we're going to say no. Primary, not so much. unless there is some sort of assistance. So really we're dealing with tertiary and secondary. Now the further complicating factor is we know how to form these things by ionizing the bond. So we can form it, we can classify it. A carbocation, if set up right, can rearrange. That means if you form a secondary carbocation, if possible, it will rearrange to a tertiary. So nature has evolved to allow that. And so these things are real, it does happen, and a little bit in organic too, we'll talk about these things as, you know, I've shown you this steroid nucleus, this tetracyclic carbon framework. Those arise from things that are just long chains. An enzyme takes that chain and folds it into a preferred conformation. These type of mechanisms happen, and then you can get shiftings of groups around from less stable to more stable intermediates. So as we wrap up here today, in the reaction, you're going to find the electrophile. You're going to classify it. And then we're going to start using some new nomenclature. The carbon bearing the leaving group, we're going to call that the alpha carbon. So we know how to ionize that. So that's going to form a carbocation of the same class of electrophile. Once you form that, you then have to look what is next door. Can we have some sort of rearrangement happen that will form a more stable carbocation? So on Wednesday, what we'll look at is doing these things that are a little bit more complex, because where you start with a leaving group may not be where the ultimate substitution occurs. And so again, that's a complicating factor of the SN1. So we'll pick up there on Wednesday. We should be able to get through everything, and you'll have your exam then.